maximum oscillator rate. Actually, normally maximum oscillator rate, if you want to find, you can use this formula. M dot is equal to rho UA. Okay, at the throat it will be maximum. You know the choking condition, right? Maximum oscillator rate at the throat is called choking. Assume this is a door. Okay, assume this is the door. So maximum maybe four. Okay, three persons can go at a time through this. Okay, so one person means easily can pass through this. Two-person also easily can pass. Three means normally they can pass. But if the four-person try to go through this door at a time, it is not possible because the three is the maximum. That is called choking. So one formula is normal rho UA. But sometime in the problem, if you don't know density and velocity, then in that case you can use this formula in terms of stagnation, pressure, temperature, also the throat area. Okay, so two formulas are there to find the maximum oscillator rate. Rho UA general formula. If density velocity is unknown, you could go for this formula. It is also available in the gas table. So again they are starting with a continuity equation. M dot is equal to rho UA. We know, so at M is equal to 1, U is equal to A, and we used to mention everything as star. So instead of U star, I am taking A star. Okay, instead of U star, I am taking A star. Now the final equation, there is no rho, there is no A, so I have to convert both. So instead of this A star, I am taking root of gamma R T star. Okay, and similarly instead of rho star, I am taking P by RT. So now substitute. Then further, so you'll get this, that is instead of rho this one, instead of A star this one, then area A star. Now further if you simplify, maybe this RT here root RT get cancelled. So remaining you will get this term. Okay, that is P star divided by root of RT star into root of gamma A star. Like that you will get it. Still further they are rearranging it, that is P star divided by root of T star, and this one gamma by R A star. Is that clear? That's what they have written here. Normal simplification and
Yes.
rearrangement. Okay, so from here to here they are writing. Now I have P star, T star, gamma R A star. So A star is there, gamma is there, R is there, but I don't want this P star, T star. Instead I need P naught, T naught. So again, the nozzle everywhere it is isentropic we are considering. Okay, so we know the relation between P star and P naught, T star and T naught. So P star by P naught is this one from the isentropic. Okay, so P naught if you take it here, you will get this equation. Then T star by T naught. Again T naught if you take it this side, you will get this equation. But here I have root T star. So they have taken root on both sides. Here instead of root they are taking power 1 by 2. Okay, so instead of P star, I'm having P naught. Instead of T star, I'm having T naught. Is that clear?
Yes, sir.
Now substitute. This is P star. This is root T star. Now see these two terms are same. That is x power n divided by x power m. That I can write it as x power n minus m. Okay, like this. These two terms I can write it. So if you write, what you will get? That is 2 divided by gamma plus 1 power gamma divided by gamma minus 1 minus 1 by 2. Then you have to do cross multiply. Then finally you will get gamma plus 1 divided by 2 into gamma minus 1 this term. Okay, so cross multiply, finally you will get gamma plus 1 divided by 2 power gamma minus 1 in the power. Okay, so these two term I'm writing like this: 2 divided by gamma plus 1 power gamma plus 1 divided by 2 gamma minus 1, and this is just I'm keeping, this also I'm just keeping. Then P naught T naught, again this also I can write the whole root. Okay, in that case, instead of this 1 by 2, I can write the whole root. That's why here I written root of gamma by r, then into 2 divided by gamma plus 1 power gamma plus 1 divided by gamma minus 1. So initially there was a 1 by 2. Instead I have taken as the whole root. Now this is your final equation. Almost all the nozzle problems we will use the isentropic relation only. Additionally, you have to find Mach number also. Okay, using that area ratio relation. So here they have taken one optimized CD nozzle which converts subsonic to supersonic without any shocks. So flow is isentropic. They are given settling chamber reservoir pressure and temperature P naught T naught. Okay, I know P naught T naught. Also AE by A star ratio they have given. Using that you have to find what is T naught, P naught, Mach number, velocity, what is static temperature, density, pressure, everything they're asking. How will you proceed? You should go to the isentropic table. So there you can find local Mach number, then corresponding M star, P by P naught, T by T naught, A by A star, everything you can find it. Okay. So AE by A star, you know, from that you can find the ME. Okay, next step, P naught 1, T naught 1 is equal to T naught E, P naught E, right?
Yes, sir.
Okay, so ME also we found, and these properties, velocity, temperature, pressure, density.
So we can use the isentropic table to find them.
Okay, so the same table, from this ratio, once you know T naught, we can find the TE, right? So assume this is AE, okay. So we know T naught E, from that we can find TE. We know P naught E, from that we can find PE. Okay, TE, PE we found it. Remaining velocity density.
So we have temperature and pressure. So using ideal gas equation, we can find density.
Okay, so we know pressure and temperature. From that we can find the density. Then finally velocity.
So we can use the Mach number velocity equation to find.
Okay, so we know gamma R TE value, ME value. From that we can find this VE. Okay. Okay, here everything is in terms of British unit. So Mach number is 2.3. Remaining normal procedure. Okay. P by P naught, T by T naught from the TPE. Then ideal gas law using density. Then using M is equal to E by A. We are finding velocity. Okay. For the same problem, they have given A star. We have to find M dot. Okay. So this problem we solved. For the same problem, they are giving A star. Using that, you have to find the M dot. Now, what is the procedure?
Yes, sir.
Okay, so you have P naught, you have T naught, gamma, R, A star also given. Okay, you can find M dot. Any other procedure? Take rho E, U E, A E. So density I know, velocity I know, then area also. I know the A star. Substitute here from this ratio, I can find AE. So again, both formula you can use it. Okay, this formula or m dot is equal to rho ua. Any formula you can use it. This I think we discussed. Okay, in this problem, again CD nozzle isentropic flow. Okay, so that is optimized nozzle which converts subsonic to sonic in the throat, then supersonic in the exit, and they are given reservoir pressure P naught. Okay, that is P naught 1. It is given and pitot pressure. So here another one P naught they have given. Okay, how to find A by A star? So through this the P naught is constant. Okay, I can say here also P naught 1. Then in the supersonic flow, if you keep on pitot tube, there will be a bow shock. In the center, it is normal shock. Correct? Then across the normal shock, there is a stagnation pressure loss. So I can say this is P naught 2. Okay. So what they have given is P naught 2 and P naught 1. I can find the ratio of it, then put the normal shock table. So we can find M1. Okay. That is here it is ME, right?
Yes, sir.
So once you know the ME, now you can go to the isentropic table. You can find corresponding AE by A star. There is a shock wave. So here I have P naught 1. Behind that I have different pressures. P naught 1, P naught 2. So from that I can find the Mach number using normal shock table. So this Mach number is 2.6. Once I know this Mach number, I can find the corresponding AE by A star from the isentropic table, 3.036. Okay. Optimized nozzle we discussed. For example, assume this is the original nozzle, CD nozzle, which converts subsonic to supersonic. Okay, so I can say here Mach number is AI inlet. This is A star. This is AE. Okay, this is the optimized nozzle. With the proper pressure ratio, I can achieve subsonic to supersonic. Sometime in the problem, so this is the original duct, okay, which converts low subsonic to sonic, then supersonic. Now assume one duct is designed like this. The same pressure ratio for the both cases, but there is no proper area ratio because it has to come up to this to accelerate subsonic to sonic. But I'm stopping here itself. Assume this is throat. Do you understand? Two different nozzles.
Yes, sir.
Same pressure ratio. It has to be like this. Okay. But instead the duct is taken like this. So we cannot say this is A star because the Mach number will not achieve sonic here. Maybe Mach number is 0.2, then 0.3, maybe 0.5, 0.7, 0.8. Here only it is achieving 1. Okay, but I have taken the wrong duct. So that in the throat I am getting some subsonic Mach number only. In that case, I should not mention this as A star. It will be AT or A throat. Is it clear? Difference between these two ducts.
Yes, sir.
Okay, this kind of problem only they have given here. So they have given one CD duct. They are mentioning AE by A throat. Okay, here to here the area ratio they are giving, and P naught 1 they have mentioned, PE they have mentioned. They are asking us to find what is the throat pressure and Mach number. If it is the optimized nozzle, then this Mach number should be the 1. Okay, they won't ask us to find. From that you can understand this is not the optimized nozzle. So it is some improper nozzle. So we have some other Mach number. Is it clear? First step. How to find it is not sonic in the throat. Then second step, any other way, how to find whether it is converting subsonic to sonic, sonic to supersonic or not. How to find? We know the P naught by P, and they have mentioned isentropic. Okay. So isentropic means this P naught 1 A will be equal to P naught E. So we know the P naught E by P ratio. Go to the isentropic table, you can find the corresponding Mach number. What is that?
Yes, sir. It's subsonic.
Okay, so if P naught by P is 1.893, then it is 1, right? If it is less than that, then pressure difference is decreasing, so it is subsonic. If it is more than that, then it is supersonic. Mach number is 0.28. So this is not the optimized nozzle. So in this nozzle, what happened means there is a subsonic Mach number. Okay. So as the flow is convergent, the subsonic Mach number is accelerated, not to 1, some other subsonic value. Again, it is decreased to low subsonic. Okay, low subsonic. Then here maybe a little bit high subsonic. Again it decreased to low subsonic. Is that clear? Okay, so I have ME. How to find this PT and MT? So here I have AI, A star, AE. Okay, in between I have different areas: A1, A2, A3, A4, and we have discussed A by A star relation in terms of Mach number, right?
Yes, sir.
This A by A star you can apply not only from this throat to inlet, it can be applied in between stations also. For example, if I compare A star and AI, I can find corresponding MI. If I compare A1 by A star, then I can find M1 at this station. Then A2 by A star means I can find M2. Okay. Then A3 by A star, all three are will be subsonic, and this will be sonic. And here A3 by A star I can get M3. Then A4 by A star I will get M4. Then AE by A star I can get ME. Like that. That AE by A star in between station also you can apply. Is that correct? Is it clear?
Yes, sir.
Okay. Now how we have the duct? Maybe like this we got the duct, right?
Yes, sir.
This what we got the duct. Okay. So if I know ME, I can find AE by A star. Okay. I know ME from the isentropic table. I can find AE by A star. Right. Similarly, if I know instead of 2 they have taken T, right? If I know AT by A star, I can find corresponding MT. Is it clear? Same way, ME if I know, you can find AE by A star. Okay. Similarly, if I know AT by A star, I can find MT. You understand?
Yes, sir.
So now I should find AT by A star so that I can find MT, then corresponding P naught D by PT, T naught T by TT, everything I can find it. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay. How to exit? See AE by okay. First ME is given. From that I can find AE by A star from the isentropic table, and AE by AT is given. Now using these two area ratio, I can find AT by A star. Maybe I have to take it like AT by AE divided by A star by AE. Okay. So from that you will get AT by A star ratio. Once you know that, you can go to isentropic table. You can find the MT. Also you can find P naught T by PT. So flow is isentropic. P naught is constant everywhere. From there you can find the PT. Is it clear?
Yes.
Yes, sir.
Okay. So first they found ME using this pressure ratio. Then AE by A star. Then we need AT by A star. Using that ratio, going to the isotropic table, they are finding MT. Then P naught by PT. P naught is known. You can find PT. Okay. In this problem, additionally, if you know T naught, also the AT, they're asking us to find M dot. Okay. So T additionally T naught is given, AT is given. From that we should find that because P naught already given, T naught now we got it. Only A star you have to find it. Simply go to this relation. Substitute AT value, you will get A star. Substitute here, you will get the M dot. Okay. The next problem. So there is a optimized CD nozzle which converts subsonic to supersonic. And in the test section, we have one wedge model with a half edge angle of 20 degree, and we know it will create the oblique shock. So the wave angle is 41.8 degree and the model is kept at 0 degree angle of attack. You have to find what is AE by A star relation. Here how will you find? Using theta beta M graph. If you know theta and beta, you can find the free stream Mach number. Here it is ME. Okay, using theta beta value, using the theta beta M graph, you can find the ME. Then you can go to the isentropic table. You can find AE by A star. That's it. Very good. So using theta beta M graph or corresponding theta beta, I am finding ME. Then go to the isentropic table. We can find corresponding AE by A star value. Okay. And here they have given AE by A star. And they are asking us to find. Okay. P naught 2 is given. You have to find P naught 1.
At
Yeah.
the
If there is a two different stagnation pressure, then there might be the pitot tube. Then there is a shock. Then how to find?
so we can find the Mach number using AE by A star.
Okay. Yeah. We know A by A star. From that you can find the Mach number here. Then
Then so using the Mach number, we can use normal shock table and find P naught.
very good. You can use normal shock table. You can find P naught 2 by P naught 1. So P naught 2 is given. From that you can find P naught 1. Okay. So from A by A star, first they are finding Mach number. Then go to normal shock table. You can find P naught 2 by P naught 1. So P naught 2 is known with they found the P naught 1. Again, optimized nozzle with the exit Mach number they have given, and M dot also given. So M dot is constant, anywhere you can take it. So using that you have to find what is T naught 1, T naught 1, then A star, then AE. Only these two are known. How to find remaining? Only ME is known, M dot is known. Using that you have to find A star, AE, P naught 1, T naught 1. And they have mentioned for sea level condition at exit. That means the CD nozzle, the flow is coming out to the CD nozzle, that is atmosphere. Okay, it is open to the atmosphere. See, they are asking P naught T naught. That means here we have the high pressure. Okay, we need the pressure difference, right, to create the supersonic flow. So this side we have the high pressure and it is open to the atmospheric pressure. Okay, so the sea level condition at the exit. So here you should take it is 1 atm. Here maybe 300 Kelvin or 288 Kelvin. Is it clear? Isentropic table you can find P naught E by PE, T naught E by TE. So PE, TE is known. You can find T naught E, P naught E, which is equal to P naught 1, T naught 1. Correct?
Yes, sir.
Okay. Next step, A star AE. Using the same
Sir,
Mach number, I can find AE by A star.
yes, sir.
Then,
And
okay, I have M dot. That is, I can find M dot everywhere, anywhere. Okay, it will be constant only. So depends upon the parameters available. You should take at which station you have to find it. Okay, so here I know pressure temperature at the exit, so I can go for rho e ue ae. Is it clear?
Yes, sir.
Because I know the Mach number, from that I can find the velocity. I know the ae, from PETE I can find rho e also. Okay, instead if you take it at the throat, everything is unknown. Rho star, u star, a star, m star. Okay, m star may be known. Okay, compared to this exit, here unknowns are more. So I can go for this exit. Okay, so rho e I can find it using P is equal to rho RT relation. Then UE, I know the Mach number. From that I can find the velocity. AE is unknown. M dot E is given 1 slug per second. Okay, we will give it in SI unit only. So rho E is known, UE is known, M dot E is known. From there I can find AE. Is it clear? Then substitute here, I will get A star, right?
Yes, sir.
Yeah. So from this mass flow rate, everything is known. I can find AE. Substitute AE here, I will find A star. So A star AE also found. So at the sea level, PE, TE they are assuming, and from that ME Mach number, they are finding pressure ratio, temperature ratio. Then substitute, you will get P naught T naught value. Then M dot at the throat or exit, anything you can take it. So for me, exit I have pressure, temperature, etc. and all. So I am finding from that first I am finding AE. Then substitute here, you will get A star. That's it. For the optimized CD nozzle, it will convert subsonic, sonic, and supersonic. And if you draw the curves, for example, this is Mach number curve, this is P by P naught curve. Okay, so optimized means initially subsonic, then it will increase to sonic in the throat. Okay, this is the throat. Then it is further accelerated to the required supersonic Mach number in the exit. Is that clear? This Mach number profile. Assume Mach number is 2. Okay, this is how the Mach number is increasing. And assume the required pressure ratio is 0.1. Maybe I already mentioned, right? P by P naught. If it is 0.528, you will get 1. If it is reduced further, then you will get supersonic Mach number. Assume P by P naught of 1.1, I am getting Mach number 2. Okay, if it is more than zero point 0.5, for example, zero point 0.7 means I will get some subsonic Mach number, maybe 0.6 something. Is that clear? For 0.528, I will get 1. If the P by P naught is less than that, I will get supersonic. If the P by P naught is more than 0.528, I am getting subsonic. That will also keep on decreasing, so that I am getting the Mach number 2 here. Okay, subsonic, sonic, supersonic without any shock. I am getting the supersonic Mach number of 2. Okay, subsonic, sonic, from the supersonic. This is the P by P naught curve, and this is the Mach number curve for this optimized nozzle. This is clear, right? These two curves.
Yes, sir.
Okay, now we will see. So instead of this 0.1 pressure, that is 10 bar pressure ratio, if you get some other pressure ratio less than that or more than that, how the flow varies along the CD nozzle, that only we are going to discuss here. Okay, if you have the proper pressure ratio, that is P naught by P of 10, okay, 10 bar difference, we will get the Mach number 2. But here we are going to study how the flow inside the duct varies for different pressure ratios. That is offline, off design conditions. This is design condition. Okay. If you keep 10 bar pressure difference and proper area ratio, you will get Mach number of 2. This is design condition. And if you take other pressure ratios, it is off design condition. Less than that or more than that. Depends upon that you will get subsonic or supersonic flows. That's what you're going to discuss here. You may ask, sir, how we can change this pressure? You remember the calibration of wind tunnel, right? So there we have some settling chamber pressure. Then we found pressure at different location along the CD nozzle. Okay. Then for the P naught and by P ratio, we have found Mach number throughout the CD nozzle. Okay. Here we got subsonic. Here you got sonic. Here you got supersonic. This you remember, right? For that you have drawn the
Yes, sir.
yeah, P by P naught, Mach number, even static pressure, temperature curve, how it varies, everything you have done in the last lab, maybe previous lab. So now that experiment, actually we have taken the reading after 3.1 second. Okay, in the normal subsonic internal also, in all the procedure, if you remember, so you will write first switch on the wind tunnel, then wait for 2 to 3 minutes to get the flow stabilized. Then you take the reading like that. We will wait for 2 to 3 minutes, okay, to get the fully developed flow. Similarly, here to build up this 10 bar pressure difference, we should wait for 3.1 second. After that only we can maintain the same pressure up to 1 minute. So our tunnel is designed in such a way we can maintain the same pressure difference up to 1 minute. So from 3.1 second to 1 minute we can maintain the 10 pressure difference. Is it clear?
Yes, sir.
Okay. Now, so 3.1 second it is 10 bar. But initially if I release this valve, maybe the next slide it is useful. Okay. If I release this valve at 0 second, there won't be pressure difference at all. Both side it will be atmospheric pressure. Atmospheric air is filled, so both side it may be 1 bar. Okay. Then maybe at 1 second there will be a small pressure buildup, maybe 3 bar. Okay, 3 bar to 1 bar. There is a pressure difference. I'll get some subsonic Mach number. Then at 1.5 second it may be increased to 5 bar. Then 2 second 7 bar, 2.5 8 bar, 3 second 9 bar. At 3.1 I am getting 10 bar. Then from 3.1 to 1 minute I can maintain this 10 bar pressure. Is it clear?
Yes, sir.
Yeah, because now only I'm opening the valve, there will be a flow just coming, so that it takes 3.1 second to build up this 10 bar. Okay, so below this 3.1 second, we can say this is the build up time. Okay, in this build up time, you can see we are getting different pressure ratios. This is how we can change the pressure ratio across the CD nozzle. Is that clear?
Yes, sir.
This is one example. So I said if I take, so this is P naught, this is maybe okay, P static pressure. So if I take P by P naught of 0.1, I can achieve Mach number 2. That is the optimized condition. Okay. If I can maintain P by P naught of 0.1, I can achieve the Mach number of 2. Is that clear? Optimized.
Yes, sir.
Now I'm going to vary the pressure ratio. Okay, which is more than that and less than that. You know, if P by P naught is 0.5 to 8, then that corresponding to the sonic. Okay, if it is more than that, you will get subsonic Mach numbers. If it is less than that, you will get supersonic Mach numbers. This is also clear, right? So
Yes,
this
sir.
is okay. This is P by P naught. This is Mach number. Okay. Now you see, initially I'm maintaining this P by P naught of 1. That means here and here I'm keeping the same pressure. Then only I will get P by P naught of 1, right? Initially there is the same pressure on both sides. If both sides same pressure, then there is no flow. Okay, flow will be due to the high pressure to low pressure. So due to the same pressure, there is no flow. Mach number is 0. I am getting just straight line here and here. Okay, now little bit I'm increasing the pressure difference, that is I'm reducing this pressure ratio. Okay, so if the pressure ratio decreases, that means this pressure difference is increases. That is clear, right?
Yes, sir.
Okay, so P by P naught decreases means the pressure difference across this duct is increases. Okay, so I'm keep on decreasing the pressure ratio. That means keep on increasing the pressure difference. Okay, so next I'm going for zero point 0.9. So zero point 0.9 means it is more than 0.528. I will get some subsonic Mach number. Assume that corresponding Mach number is zero point 0.1. So what will happen because of this reduce increase in pressure difference? The flow will little bit accelerate in the throat up to throat section. Okay, this is convergent nozzle, right? So subsonic will get accelerated in the convergent. It will accelerate up to maximum throat. Again, this is divergent duct. So subsonic flow will get decelerated in the divergent duct. So you can see the Mach number. The Mach number is accelerated up to the throat section, that is convergent duct. Then from there again it is decreasing to the Mach number of zero point 0.1. Okay, for the pressure ratio of zero point 0.9. Is it clear?
Yes, sir.
Now further I am reducing this pressure ratio to zero point 0.8. That is pressure difference I am increasing. Hmm. So now assume the corresponding Mach number is zero point 0.3. So what happens? The Mach number is little bit further accelerated, but still it is subsonic only. Then again it is decelerated in the divergent duct. Okay, convergent duct will accelerate the velocity, divergent duct will decelerate the velocity. This is for subsonic case. Okay, now again further I am reducing the pressure ratio. Assume the corresponding Mach number for this pressure ratio is zero point 0.7. Okay, so already the subsonic Mach number is increasing. So assume for this zero point 0.7 I am reaching sonic in the throat. Okay, I am keep on increasing the pressure difference, that is decreasing the pressure ratio. What happened? Now the flow reaches sonic in the throat, but here exit pressure ratio is less and the corresponding Mach number is zero point 0.5. So what happened? It is again decreased to zero point 0.5. Okay, and this condition we are calling as choking. Maybe for this condition I am getting choking. So the whenever I increase the pressure difference or decrease the pressure ratio, the flow get accelerated, and maximum it can accelerate to 1 in the throat, and that condition we are calling as choking. Maybe for this pressure ratio I am getting the choking. Now further I am reducing the pressure ratio. Okay, and corresponding Mach number is zero point 0.6. So already the duct is accelerate the flow to the sonic. Okay, further I am reducing the pressure ratio. That means increasing the pressure difference. So in that case, what will happen? It will already it reached sonic rates. It will be further. It will be accelerated. Okay, maybe uh, here I have some zero point 0.2 Mach number. For this zero point 0.7 pressure ratio, the Mach number reach 1. Again, it come down to zero point 0.5. Now further I am decreasing the pressure ratio. What happened? Already it reached sonic, and it is further trying to accelerate to some supersonic Mach number, maybe for 1.2. Okay, assume because of further reduction in pressure ratio to zero point 0.6, the Mach number is little bit accelerated to supersonic in the duct. But the exit Mach number, corresponding Mach number, if you see, it is only zero point 0.6. So here I have Mach number 1.2. Here I have 1.6. Sorry, zero point 0.6. Now what will happen? There will be a normal shock wave, which converts 1.2 to maybe zero point 0.8. Then that zero point 0.8 will be further decelerated to zero point 0.6. Okay, so then there is a normal shock which convert 1.2 to zero point 0.8. That zero point 0.8 is further decelerated to zero point 0.6. So I should not draw the straight line because there is a deceleration. So from zero point 0.8 to zero point 0.6 it goes. Is it clear?
Yes, sir.
Okay, so for this ratio, choking occur, that is m is equal to 1 at the throat it reached. So whatever further I decrease, then the flow will try to accelerate to the supersonic in the divergent duct. So for the zero point 0.6, I achieved 1.2. Then the normal shock convert that into zero point 0.8 and is further decreased to zero point 0.6. Now further I am decreasing the pressure to 0.55. Now what will happen? It will be further accelerated to maybe 1.5. Okay, maybe now further it is accelerated to 1.5. Then there is a normal shock wave which will convert that into the zero point 0.9, that may be reduced to zero point 0.7. Okay, it is further accelerated to 1.5. It may be reduced to zero point 0.9. It will be further reduced to zero point 0.7. Like that, after choking, if I keep on decrease the pressure ratio, that normal shock will move towards the exit. Previously it was here. Okay, now it is moving towards the exit. So at some point the normal shock will be at the throat, then it will be vanished. Okay, it will be swallowed. Is that clear?
Yes, sir.
Okay, and keep on, if you decrease this pressure difference, so what will happen, this normal shock strength also decreasing. Like this, finally it is in the throat, then it will be swallowed. So this is in this subsonic region. Now we will come to the supersonic region. Okay, this is over. Now assume I have this what is it, pressure ratio of zero point 0.4 and the corresponding Mach number is 1.5. Now what happens? The duct is designed for Mach number 2. Okay, so what it will try? It can maximum accelerate Mach number of 2. Okay, it cannot accelerate more than that. Now see, the outside pressure is zero point 0.4, so I should get it is 1.5. So above this, what happened? The flow got accelerated to 1.2, 1.5, 1.8, like that. It is keep on accelerating. At some point, there is a normal shock wave in the throat. Then that also swallowed. Okay, so already in the duct, the Mach number 2 is achieved. Okay, is that clear? So above this case itself, there is a normal shock that keep on moving towards the exit. At last, the normal shock is swallowed. So there is no normal shock, but the Mach number reaches 2 already. Now further I am decreasing the pressure ratio. So for that the exit Mach number should be 1.5, but the duct already it accelerated the Mach number to 2. In that case, what will happen? There will be a oblique shock wave. That oblique shock converts this Mach number 2 to 1.5. Okay. So this curve hereafter will not vary because the duct already accelerated to the Mach number 2. Then for this condition, there will be a oblique shock wave which converts Mach number 2 to 1.5. Okay, further I am decreasing to zero point 0.3. So for the zero point 0.3, the corresponding outside pressure is 1.8. Okay, again same oblique shock wave, but the strength will be decreasing. Previously it convert 2 to 1.5, so strong oblique shock. Now as the pressure difference decreases, now it converts 2 to 1.8. So same oblique shock, only the strength is decreasing. You can see the angle. So here it is more angle, here it is less. Okay, that is to the free stream only you have to see, right? Here angle is more beta, but here the angle is reduced. Okay, so from here to this optimized condition, we will get the oblique shock wave, and if you keep on decrease the pressure difference, the shock wave angle and shock strength will keep on decrease, which will convert high supersonic to low supersonic. Is it clear?
Yes, sir.
Okay, so in this region, oblique shock wave. Then if I maintain 0.1 pressure ratio, there won't be any shock etc. and all. Simply subsonic will be accelerated to supersonic without any shock wave. Then further I am reducing the pressure ratio. For that pressure ratio, assume the corresponding Mach number is 2.5 outside. But this duct can accelerate maximum of Mach number 2. Now what happened? 2 to 2.5 it has to increase. Then there will be a expansion fan which accelerate 2 to 2.5. Okay. So this is optimized. There is no shock. Before that there is oblique shock. Further if you decrease there will be expansion fan. Okay. And here there will be a normal shock and here simply subsonic flow. Is it clear?
Yes, sir.
So over expanded means there will be a oblique shock. Oh. Okay, this you can remember. Otherwise, always it will confuse you. Over expansion means oblique. Oh. And under expansion, it is expansion fan. Okay, so once if you remember this over expansion oblique, this you can clearly write it. This is optimized. Otherwise, design condition, no shock. This is sonic, and before that it is subsonic. Here it is supersonic, and here I may get throughout the duct subsonic flow, or I may get the normal shock with a subsonic. Is it clear? Very low means simply subsonic. After this point, there will be a normal shock which will convert the subsonic. Like that, finally I will get the subsonic, and this is sonic, and here I will get supersonic associated with the oblique shock wave. And here there is no shock at this point. Then below that also I will get supersonic flow, but there will be expansion fan. So this is clear. Now we will see this region. What happened? Already the duct is accelerating the flow to Mach number 2, but outside the pressure ratio is not proper, so I am getting 1.5. Now even we can say we can name the pressure. I am naming this inside the exit pressure is PE and this atmospheric pressure is PA. Okay, so exit pressure is PE, that atmospheric pressure is PA. Now what happened? Due to this Mach number difference, there is a oblique shock. So for this pressure ratio of 0.4, I should get only 1.5. But the duct is designed in such a way, it is accelerated to 2, that is over expanding. Okay, what I need is 1.5, but the duct is expanding too much. It is over expansion. Is it clear?
Yes, sir.
That's why we are calling this as over expansion, because outside what I need is the 1.5, but the duct is accelerating to the too much level, that is over expanded. So over expansion means there will be oblique shock. That's why we are calling this as over expanded nozzle. Is that clear?
Yes, sir.
Now this region if you see, so according to this pressure ratio in the outside I should get 2.5, but the duct is designed for 2. Okay, I need 2.5, but it is accelerating only to the 2, that is less acceleration, less expansion. So we are calling this as under expansion. Is that clear?
Yes, sir.
So there is a expansion fan which convert 2 to 2.5. Okay, so can you first say for the over expanded nozzle how to relate PE and PA,
So
which
PE is
is
greater than PI.
PE is greater than PA. Wow. So over expansion means, okay, here I have PE, here I have PA. Over expansion means there is a oblique shock, right?
Yes, sir.
So what is the purpose of oblique shock? What it will do?
So PA will be greater than PE.
Yeah. So oblique shock means it is a compression wave. It will compress the flow so that pressure will be high behind it. So for the over expansion nozzle, PE will be less than PA. Is that correct? Do you understand or should I repeat it? Even in terms of Mach number, if you see, I said this is accelerated to 2, but outside pressure is such a way I am getting 1.5. Mach number is 1.5. You know, if the Mach number increases, pressure will decrease, right? So here it is 1.5, here it is 2. So here better acceleration. So here it should be less pressure compared to this 1.5. Is that clear?
Yes, sir.
So anyway, using Mach number comparison or using this shock wave, you can find the pressure relation. So I prefer the shock wave. It is very easy. So over expansion means oblique shock. Okay, that means here we have the oblique shock. So here we have PE, here we have PA. The purpose of the character of the oblique shock is to compress the flow. That means this PA will be more. So PE is less than PA. Is that clear?
Yes, sir.
Then the same way we can go for the under expansion. So under expansion, that means there will be a expansion fan. Okay, so here I have PE, here I have PA. Now can you relate for under expansion? So the purpose of expansion fan is to accelerate the flow. Okay, if Mach number increases, definitely pressure will decrease. So PE greater than PA. Okay, so one is oblique shock, another one is expansion fan. So oblique shock compresses the flow, so PA is higher, but expansion fan accelerate the flow, so PA will be less. So PE less than PA, here PE greater than PA. Is that clear?
Yes, sir.
This expansion wave strength, can you say if I keep on decrease the pressure ratio, this expansion fan strength will increase or decrease?
Will increase, sir.
Very good. Because this is the oblique shock. Here I have 2. 2 is converted to initially 1.5, then it is 1.8. So the shock strength is decreasing. That is for the oblique shock. But here what happened? If I keep on decreasing this pressure ratio, I may get 3, 4, 5. So here I have 2. Then there is an expansion fan. Okay, expansion fan. That expansion fan is converting that 2 to 2.5, then 3, 4, 5. That means expansion fan strength is increasing. Is it clear?
Yes, sir.
Okay. So for decrease in pressure ratio, oblique shock strength is decreasing, but expansion fan strength is increasing.